Alright, let's go ahead and start this first video for Unit 4, which is about the electron and how the electron exists around the nucleus. What I want to tell you is this first lesson for this unit, it takes a moment to grasp it. And so this is what I want to encourage you about. I want you to watch this Edpuzzle. I want you to pick up all the little details, as many little details as possible. And as we go along, a lot of the blanks will start to fill in, a lot of the things that you're not sure about, and I promise you that at some point it'll all start to come together. I don't expect you to fully get everything through this Edpuzzle, but I do expect you to get as much as possible, and then when we go into class, we're going to really highlight and re-teach a lot of this, okay? So just make sure that you are really following along. So let's go ahead and get started. Electron orbitals are locations where electrons are found, and it's within the electron cloud. And so there's different types of orbitals that are within an energy level. And so when we think about an atom, we think about, okay, here's the first energy level, here's the second, here's the third, and so on. And so we think about an atom like that. And so within each energy level, there's actually different types of orbitals within each energy level. For example, the second energy level has s orbitals and p orbitals, and we're going to talk about that in a moment. But the point here is that in a given energy level, again, for example, let's say this second energy level, you can have different types of orbitals. We're going to learn about those different types of orbitals. Now, each orbital, something to keep in mind, each orbital can hold a total of 2 electrons. This is very important. Keep that in mind. Every orbital can hold 2 electrons. Now, let's go ahead and talk about the 4 types of orbitals that exist within an atom, all right? So exist within the electron cloud. The first type, they're called s orbitals. Now, s orbitals have a spherical shape, so they're shaped like a sphere, and they have a total of 1 orbital. So s orbitals have 1 orbital. Again, we're gonna talk about this as we go, so just pick up as much as you can. Well, how many total electrons can go in the s orbitals then? Well, there's 1 electron right there. And how many electrons can go in an orbital? 2. So if we have 1 orbital, 2 electrons can go in each orbital. That means that there's 2 electrons. S orbitals can hold a total of 2 electrons because there's only 1 orbital. It'll make more sense as we go. These are considered low energy. And here's maybe a picture of it. It's like a sphere. The next type of orbital they're called p orbitals. P orbitals are shaped like peanuts. Now, s orbitals have 1 orbital, p orbitals have 3 orbitals. All right, so they have 3 orbitals. Well, how many total electrons? Well, each orbital can hold 2 electrons. So how many total electrons can go into those orbitals if there's 3 orbitals? Total is 6. Because again, there's 3 orbitals, 2 electrons can go into each orbital, and so there's a total of 6 electrons. And these are the shapes of those p orbitals. I'm going to go ahead and say that this is the second lowest energy. It's the second lowest energy. Now, the next one is d orbitals. D orbitals are like daisies. Okay, look like daisies. See, looks like a daisy. And there are 5 orbitals in the d orbitals. So the d orbitals have 5 orbitals. So how many total electrons? Well, again, 2 electrons in each orbital. There's 5 orbitals, so that is 10 electrons. And these are the third lowest energy, so they're actually kind of high energy. And then the last one, they are the f orbitals. Those have a funky shape. And I want you to guess how many orbitals. How many orbitals do you think there are? And I'll let you know there's a pattern. So look at what the pattern is. It goes 1, 3, 5, and 7. Okay, well, how many total electrons then can go in the f orbitals? Well, you can get a total of 14. And so this right here is really important because it's going to help us understand the periodic table. This right here is really important as well when we're talking about electron configurations. And this is going to be the 4th lowest, which makes it the highest, really. All right, let's go ahead and move on here. Let's take a look at this periodic table. So before we take in these notes here, I'm gonna really take a look at this periodic table. Notice how the s orbitals have one orbital. They have one orbital, and they have 2 electrons. And so you can see, we're going to talk about the fact that it has 1 orbital and 2 electrons. So let's go and see where the s orbitals are. On the periodic table, these are the s orbitals. You can see that these are the s orbitals. And what I want you to notice is how many columns are there. There's 1, 2 columns. The reason why there's 2 columns is because there's 2 electrons in each s orbital. So these are the s orbitals. Notice how there's 2 columns. Okay. Also notice how this right here is helium, and helium, even though it's on the right side, is actually a part of the s orbitals. All right, let's go ahead and talk about the p orbitals. The p orbitals have 3 orbitals. They have 3 orbitals, 6 electrons, and so if you take a look, the p orbitals are right here. And again, there can be 6 electrons. There can be 6 electrons. Notice how it's 1, 2, 3, 4, 5, 6 columns in the p orbitals. So the p block is called the p block. There's 6 columns in the p block because there's 6 electrons that go in the p orbitals. So we call this the p block. And there's a pattern here. So again, the s block has 2 columns. The p block has 6 columns. All right, how many columns? So again, the S block has 2, the P block has 6. How many columns do you think the D block will have? The D block, you'll see, has 10 columns. And this right here is the D block. And if you take a look, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns. And there's 10 columns because 10 electrons go in the D orbitals, and so that's the D block. All right, well, how many electrons do you think will go, or how many columns do you think there'll be in the F block? Well, again, there's 2 in the S, there's 6 in the P, there's 10 in the D, and there's 14 in the F. And if you take a look, this right here is the F block, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that's the F block. So we have the S block, we have the P block, the D block, and the F block. And the columns actually represent the number of electrons that are in each one. So let's go ahead and talk about electron configurations. Electron configuration. So electron configuration shows what electrons are in each orbital, and so it kind of shows you the location of each electron within an atom and within an element. And so there are 3 rules that we want to consider. The first rule we want to consider is called the off-ball principle, and what that states is that electrons will fill the lowest energy possible before they go up to another one. In other words, they'll fill the first energy level before they go to the second. They'll fill the third, then the fourth, then the fifth, and so on. And so they fill the lowest energy possible. Now, they'll also fill the lowest orbital possible as well. So S orbitals will get filled first, P orbitals second, D orbitals third, and F orbitals fourth. And so those will get filled in that order as well. Let's not worry about this here. The next one is the Pauli exclusion principle. The Pauli exclusion principle states that each orbital must contain 2 electrons of opposite spins. And so we're going to talk about this in a moment, but we're going to represent orbitals like this, and we're going to talk about how an electron can have an up spin or a down spin. And in an orbital, again, there's 2 electrons per orbital, One will have an up and one will have a down. And that's the Pauli exclusion principle. And then Hund's rule, again, we'll talk about this as we go. Hund's rule states that one electron will go into each orbital before they pair up. And to give you an example, again, we'll fill in these blanks as we go, but if we have the p orbitals here, and we're going to represent them like this, there will be an electron in each orbital before they pair up like this. So when we are writing the electron configuration for an element, what we're trying to do is we are trying to show where every electron is within the electron cloud. Let's go ahead and, for example, let's say we want to do the electron configuration for silicon. Well, if you look at your periodic table, this is where silicon is. So silicon's right there. And so what you need to do is you need to account for every electron for silicon. Now, silicon has a total of 14 electrons, and so when we write the electron configuration, we're going to do it for that. So again, this element here is really right here. So helium is a part of the s orbital. So what we do is we're going to write 1s. And so we're going to write 1s. Now the s orbitals have one orbital. And the way that we write the orbitals, we put a line above it. Now let's go ahead and break down what I just wrote there. So this 1 right here represents the energy level that the element is in, or that the electron is in. This here represents the block, which happens to be the s block. And then this represents the orbital within the s orbitals. And again, s orbitals have one orbital. What comes after the 1s's, if you take a look, are the 2s's. So those are the 2s's. And we put a 2 there, put an s. S orbitals have one orbital. Now, what comes after this particular element there? Well, this element is element number 4, and if you look at your periodic table, element number 5 is this one. And so what comes next is this set of orbitals, which those are the 2 p's. And so the p orbitals have 3 orbitals. And so what you'll end up doing is writing 3 orbitals like this. Again, each line represents an orbital. After the 2 p's, so after this comes the 3 s's. And then what comes after this comes the 3 p's. And we actually are going to stop right there because silicon is in the 3 p's, and so we only need to go to the 3 p's. Now again, according to the Aufbau principle, all electrons will fill lower energy levels first before they go to before they move up to a higher energy. And so silicon does have a total of 14 electrons. And we typically write the setup like this, but I'm going to put these lines here. These lines that I'm putting are not typically a part of it, but I think that it's makes it to where we can see the different orbitals there. And so essentially what needs to happen is this needs to fill before this one. And the 2 s's need to fill before the 2 p's get filled. And the 2 p's need to get filled before the 3 s's, and the 3 s's need to get filled before the 3 p's. And so they need to fill in order. And when you are writing electrons, each orbital, again, is going to have 2 electrons. Very important. Each one's going to have 2 electrons. And what will end up happening is we're going to put an electron here, and we represent an electron by an arrow. So that is an up arrow. And then we put a second electron there using a down arrow because they have opposite spins, which is the Pauli exclusion principle. You cannot have this. This is not okay. You can't have that. Instead, you have this. So again, the 1 s's will fill before the 2 s's. So now the 2 s's will fill. And so this is the 3rd electron here. Again, up arrow. This is the 4th electron. Now when we get to the 2 p's, again, the 1 s's need to be filled and the 2 s's need to be filled before we get to the 2 p's. But something new is going to happen in this situation. According to Hund's rule, Hund's rule states that when you have a situation like this where you have multiple orbitals within a particular sublevel like that, what will happen is this will not happen. This will not happen where you'll have one up arrow and then one down arrow, where you have one orbital. This is one orbital right here. Well, you'll have one orbital fill first. Instead, what happens is each orbital will fill we'll get one electron first, and then what happens is they go back and then they pair up. So again, I'm going to go ahead and redo that. What happens is it goes up arrow, up arrow, up arrow, because again each one gets filled, and then it goes down arrow, down arrow, down arrow. Now in the end, this looks like it might be the same outcome, because look at the way it is right now, and versus if I do it like this. So if I did it this way, it would end up with the same outcome. However, there will be a situation where it won't end up with the same outcome, and we will see that in a moment here. So the two P's get filled, and let's go ahead and pause here. So far we have 10 electrons. That's 10 electrons. Silicon has a total of 14 electrons, and so there's there's 4 more electrons that we need to fill. Again, we have this here filling before the 3 P's. Now when we add this here, now we have a total of 12 electrons, and silicon has a total of 14 electrons, so we need to fill 2 more electrons. And again, when we do that, we're going to go up arrow, and we actually stop right there. The reason why we stop right there is because silicon has 14 electrons, and so there is not another electron to do that. And so notice how this is actually going to be the final electron configuration. What I will say is, if we were to have done this, we would end up with, where we did up arrow, down arrow, we would end up with this situation, which this is not correct. That's not correct, because each one of these needs to be filled before they start to pair up like that. And so this is electron configuration for silicon. Let's go ahead and do another practice problem. All right, let's go ahead and do the electron configuration, the orbital notation for sodium. And sodium is right here on the periodic table. And so what we're going to do is we're going to write out the orbital notation for that. So again, we have one S. S's have one orbital. We have 2s. We have 2p. We have 3s. And we actually stopped there. The reason why we stopped there is because sodium is in the 3s's. And so sodium does have 11 electrons. So we need to show where those 11 electrons are. And so we have 1, 2, 3, 4. Again, this needs to fill before this one fills. This one needs to fill before that one can fill. All right, so we have 1, 2, 3, 4. And then when we get here, it goes 5, 6, 7, 8, 9, 10, 11. And this is the electron orbital notation for sodium. Now, let's go ahead and take a look here at a couple things. All right, so something I want to point out here is that notice how this here, the 3s's, has 1 electron. And that's because sodium is right here, and it's 1 element into the 3s's. Let's take a look at the problem we did before. Notice how the 3p's here have 2 electrons. And notice how silicon is 2 into the 3p's. So this here, we can actually predict, this happens to be fluorine. If we were to do the orbital notation for fluorine, the ending would be 2p. And then we would have 1, 2, 3, 4, 5 electrons in the two p's. So it would go 1, 2, 3, 4, and 5. And so you can sort of start seeing how many electrons will fit into those. We're going to go ahead and take a look at some other things here. So let's not worry about that. So let's go ahead and take a look at these here. All right, so we have 3 different electron configurations, and what we're going to do is look at them and try to identify the element that they are. And there's 2 ways to do it. The first way you can do it is by looking at this. So you can look at this, and you can count how many electrons there are, because again, every arrow represents an electron. So we have 1, 2, 3, 4, 5, 6, 7. So there's 7 electrons there. And so what element has 7 electrons? Well, it happens to be nitrogen, which if you look over here, nitrogen is right here, and it's got 7 electrons. Now the other way you can do this is, and this is the way that I would suggest you do it, is just by looking at the last part here. So you just want to look at the last part here. So notice how it's the 2 p's, okay, so we know that it's in the 2 p's, and it's 1, 2, 3 electrons. There's 3 electrons into the 2 p's, so it's 1, 2, 3 elements into the 2 p's. So let's go ahead and do this next one. Well, let's look at the last one here. So here's the last part. Notice how there's 2 electrons here in the 2 p's. So in this situation, we know that it's going to be 2 electrons into the 2 p's. So here are the 2 p's, and it's 1, 2 electrons into the 2 p's. So what elements is that? That's carbon. All right, what about this one? Well, it's in the 3 s's. It's 1 element into the 3 s's, so it's right there. So let's go ahead and look at these last parts of orbital notations here. So let's just say that this is the last part of the orbital notation.
Hey, we're running the answers, right?
So let's go ahead and take a look and pretend that this is the last last part of the electron configuration. Well, we know it's in the 3Ds, and how many electrons are there? There's a total of 6 electrons there. If you count them, there's 6 electrons. And so here are the 3Ds, and it's 1, 2, 3, 4, 5, 6 electrons. And that happens to be iron. Now, something I want to point out, notice how there's something different about the d orbitals. Notice how this is in the 2nd energy level, and that's 2 s's. This is in the 3rd, and that's 3s. This is 3p. This is the 4th energy level, and this is 4s. However, this is not 4d, it's 3d. This is the 5th energy level, and it's 4d. And so the d orbitals, if you take a look, the d orbitals actually go down by 1. So even though this is the 6th row here, this is the 5d. So what I want you to do is pause real quick, and we've got this here and this here. I want you to figure out what elements these are. So pause this real quick. Again, we determined that this was iron. I want you to look at your periodic table and actually practice this and see if you can come up with the right answer for this. So go ahead and pause and do that. All right. Let's go ahead and see what elements these are. This here is in the 4 p's, okay? Here are the 4 p's, and it's got 5 electrons there. It's got 5 electrons. So it's 1, 2, 3, 4, 5. And that happens to be bromine. So the answer to this one is bromine. All right. Go ahead and pause the video again, see if you can get that last one. All right, well, this is the 3 p's. It's 1 electron into the 3 p's. So here are the 3 p's right here. It's 1 electron, which is right here, which is aluminum. All right. We have these 3 different electron configurations. And there's actually something wrong with all 3 of them. there's something wrong with all three. This is the last thing I'm going to ask you. I'm going to ask you to pause this video, and I'm going to ask you to figure out what is wrong with each of them. Alright, so here's the answer. This here needs to be filled completely before this one is filled. Now if you take a look, we have a total of 6 electrons there, and so what essentially happens is this one can't be there, it has to be here first, so that has to be filled before the 2 p's get filled. Alright, the second one here, if you take a look, this has 3 arrows in this orbital. It cannot have that. 2 electrons go in each orbital. So again, 2 electrons can go into each orbital. You can't have 3. And so this here really should be a down arrow right here. And then this last one, within a set of orbitals, you have to have each orbital filled before they pair up. So I know that this was a lot of information. We're going to practice this in class, and the more we practice it, the easier it gets. I think it's not too bad once you get it. Feel free to email me if you have any questions, and I hope you have a great weekend and a great day.